The first speaker this afternoon is Major Jeffrey Woolford from the United States Air Forces in Spangdahlem. And he's an A-10 pilot physician and is going to talk to you about controlled flight into terrain. And we have, of course, a question for you. So take out your clickers, make sure they're turned on. And the question we would like you to answer is, airplanes suffer from so many technical faults that it is only a matter of time before any reasonable man realizes that they are useless. Ooh. Well, let's see what you say afterwards. Major.
Thank you. That was interesting. I wasn't expecting that response. So I get the coveted after lunch session, so we'll see how well I can keep everybody awake here. Generals, my colleagues in the aviation medicine, thanks for having me today. Colonel Coakwell, thanks for the opportunity to come in and speak on this topic. I think you'll find it interesting. CFIT, even in itself, it says controlled flight into terrain. It seems like an oxymoron, like why would anybody do that, right? Well, we're going to start walking through it. I want to give some acknowledgments to the individuals and the organizations that made this research become a reality over the last nearly 30 years. But there is one European colleague here, Sweden, that put a substantial amount of research and testing and development into this, who's not represented on the screen. And if it's not the F-16s, it will be the Gripens, from what I understand, that you'll first see this implemented into their flight control system. Slide, please. Okay, so one of the unique things that we have as aviation professionals and doctors is we have to learn how to speak two languages. So we got a softball question in the beginning, which, by the way, was a historical question from 100 years ago. Throughout this, I'm going to test your knowledge on being able to speak both languages. And then there's also a real question, as if you were taking your boards. So here's the introductory. I'll give the example. What does VFR mean? It depends how you look at this, right? Next slide, please. To the pilot, right? To the doc. Visiting friends and relatives. You should have saw my face in my internship when they said VFR to me, and I looked out the window, and my attending said, "What are you doing?" I said, "Forget it, sir." So it was a whole different world. Next slide, please. Accountability, of course. This was cleared by Davis Monthan Public Affairs to make sure everything that we're going over today is open source. So next slide, please. I'm going to try to teach you after lunch. That's the gist of this slide. So we'll see what happens. Next slide, please. The real graduate level question. I will give you the answer at the end of this presentation, but if you'll take a moment to chew on it and think what you think the actual numbers are. Everybody have your answer? Next slide, please. I think it's interesting that this technology, they started to develop this in 1984, or 82, excuse me. And just a year and a half ago, it was the lead story for Aviation Week in space technology. It's been there. We know we can save lives, and I'll let you read the quotes for yourself. However, perfecting protection, it's time that we actually implement some of the flight control system and a thinking plane into the human interface. But it doesn't end in 2010. This same writer obviously assigned this concept, this topic. Next slide, please. Just last November, came out with an update to this. And this is very, very important because the changes that have happened to the program in the last year and a half include, in the States, there's a new program called the Android, a small cell phone. That Droid phone has the capacity now to to hold all of the DTED data from the entire world. So the digital terrain data is on one cell phone, which is remarkable because now the portability makes the value of this program even more reasonable in times of tight recession. Next slide, please. So our overview of what we'll go over today. Next slide. So we have to start with a definition. CFIT define. Controlled flight into terrain. Obviously, as we say in our briefs when we fly, don't hit the ground and don't hit anything hooked to it. This is what we would all traditionally believe to be CFIT. Next slide, please. It's also important to understand, though, that there is a moment before collision with the ground or anything hooked to the ground that pretty much you've already committed to a collision. And that's where this system works. It's in the realm of what's getting ready to happen, what's predicting, like predictive ground collision avoidance system, or PGCAS. So next slide, please. Before we start this tape, well, it's going to start. I'm going to show you how quickly these things can go wrong. And this is one of our US Thunderbird pilots out west. And I'll show you how quickly he has to make that ejection decision. But please understand, it was a simple mathematical error. That is, once he committed the backside of the loop, he was already committed, and we've entered this realm of CFIT. If you could run it, please. There. He's gone. Happens quick. Over the top, as we all learn in pilot training, you have to decide whether you have enough airspace to finish that maneuver. He didn't, and then he lost the jet. So the numbers don't lie. I'll let you go through this. Of course, this is US historical data, 28% of pilot fatalities and 22% of destroyed aircraft. And of course, again, in times of tight money, you just can't let one of those horses go. The study that I'm going to reference here, you'll see down on the bottom, the automatic collision avoidance, I can't read that there, system business case. Thank you, sir. That's from 92 to 2004. So a lot of this data is just retained with that study. However, I'll update a bit more. Next slide, please. And then again, another quote from the same study. The leading cause for loss of lives, the most important thing. And then combat capability. Next slide, please. $3.7 billion, 86 pilots, 9 squadrons. 9 squadrons. Can you imagine that now, trying to fund that? That's more than some of our allies and our peers have. Next slide, please. Yesterday, General Travis spoke a little bit about top-down leadership on this topic of setting priorities. And going back to Secretary Rumsfeld, you'll recognize that, as we mentioned yesterday, at least a 50% reduction in safety. Well, note that date there, it's 2003. So there was commitment from the top on down, as well as building upon the recognition that the research proved that this was a possibility. Next slide, please. So we'll go through the acronym cascade, but what I want you to see is the connection of where it started from the bosses on high all the way down to the enterprising individuals that figured out how to make this happen, and leading to the case that we've referenced throughout this. Next slide, please. So there's the copy of the case if you're curious, and you can get it out there in open source. But their recommendations in 2006, and again, I won't insult your intelligence and read it to you, but the system not only is to warn the pilot, like we have now, but it is to fly the aircraft out of danger. That is a big, big shift in the way we think about controlling an aircraft. Who's actually in control? Do we have Christine at that moment, which is the general consensus amongst the operators? Next slide, please. The leading cause of death. Again, training the human is a very, very labor and time-intensive process. The second leading cause of losing horses, if you will. Next slide, please. So here's the mandate. We will put something, automatic collision avoidance technology, ACAT, and then also there's a caveat on that being the ground collision avoidance technology. We will do this. That was the mandate, 2006. Next slide, please. So, now that I gave you the first one, AFB, any guesses? You can shout them out. Sure. Now that, next slide, please. Very good. Okay, next slide. Three elements, of course: policy, training, and technology. Pretty standard, right? How to go about things. Next slide, please. We'll break it down. I won't drag you through it all, but of course the Federal Aviation Administration for our civilian sector, as we've heard about in this seminar, and also the U.S. Air Force, United States Navy. They all came out and said, we're going to do this. Next slide, please. Members of ASMA in the group will recognize the resolution that also said, amongst those of us that focus on this in medicine, we believe this is the right thing to do and what needs to be done. Next slide, please. So, training. There's only so much that a human being with human reaction time is capable of overcoming. And these are various reasons why. Of course, we know GLOC. Loss of control in flight. Spatial D, we've talked about a little bit. Target fixation, we've not mentioned, but is a real thing, as you get those fangs out and you want to take out that tank, or you want to help the ground commander, which is what we're here for. Sometimes you realize after you finish that strafe and you let go of the trigger, it's too late and you've already committed to a collision with the ground. Next slide, please. When we briefed to fly at least in the A10 community, we have these time to die charts, and we have to call it a time to die chart in our brief. And that's to show you the simple mathematics of a 1 degree or a 2 degree nose down, whether you're rolling, how much time you have to look down, and with the way the ergonomics are set up in a cockpit, if you have to put in a 10-digit coordinate, how much time do you really have to look down and type something before looking up again? So these are the time to die charts out of our books that we brief to on every flight. Next slide, please. All right. This, I want you to pay attention very clearly to this spot right here. That is the radar altimeter. I'm hoping with the lights dim you can try to watch this real time. I want you to watch it. It happened out at weapons school, Nellis Air Force Base. It's going to take about a minute or so, but it's worth it. Watch this and tell me if you recognize early enough what's happening with this pilot. That's not it. That's not it. Those are two legacy rays. You can stop that tape if you would, please, and we'll go to the next one now. If you didn't see it, we're going to slow it down. I want you to read that radar altimeter. Tell me what you see. Obviously there was a false, they couldn't separate the near and the far horizon, correct? Right? Next slide, please. The radar altimeter on our plane is on the empennage of the tail. If he was in any bank at all, he would have hit the ground. To give you an idea how quickly this happens, obviously he's thinking about the target where he has to be, not so much where he is in space. It's time for the plane to help us do that. So, ground proximity warning, TALS data, all these predictive GCAS, all these acronyms, they're there to warn the pilot, but if the pilot is overcome, whatever's going on with distraction, it doesn't work. Advisory only. It is time to move on to something that does more. Next slide. This I thought was very interesting in the studies. Common misperceptions. The community, the pilot community argued we don't need to do it, and here's the 3 reasons why. I'll let you read them quickly. However, there's been studies for years, going back to when I was born. I was 6 months old, and I'm going to show you. Next slide, please. This was a study done by a fellow pilot physician, Pete Makes, and Colonel Makes is now retired. This is one of the resolutions of his study where he found out that recency and currency really did not matter regarding CFIT. It didn't make a material difference whether an individual was going to suffer one of these. So we'll go to the next slide, please. That was 2006. I was 6 months old in August of '71, and look at this. They were talking about it before in currency. So nothing's changed in my lifetime. We've known this, but we've not acted on this as a community. And that's what started the studies in the early 80s. Next slide, please. What's MAP? Okay. Next slide, please. Missed approach point. They're both important, right? It just depends where you happen to be sitting that day. Next slide, please. So the requirements. Again, we won't go through the details, but when they sat down in the 80s and said, what do we need the system to be able to do? These were the 3 big ones. Stringent integrity was important because if the system became unreliable and the operators recognized it was unreliable, it was no good. They were simply going to shut it off. It was an option, right? You just start ignoring it. Next slide, please. 84 all the way through to 2000. The work was done by diligent teams to make sure that the technology was there when we were ready to implement it and use it, which we haven't yet. Next slide, please. Thanks to our friends at NASA, we were able to get a complete detailed database. 80% of the world was mapped with reasonable fidelity, and I'll show you some exclusions to that. However, instead of using the old terrain following radar, we were able to use DTED data, which is what made this possible. Of course, navigation systems were updated to embedded GPS, INS, etc., over legacy systems. Next slide, please. That's the big picture in your mind. Just recognize roughly a 10 foot or 10 meter by 10 meter square on the ground is what each of those green dots represent. Next slide, please. Bit of an eye chart, but what I want you to pay attention to is on the far side, you'll notice the flight control autopilot, once it knows what has to be done, it simultaneously tells the pilot and then commands it. It doesn't give the pilot the option first to let that happen. Next slide, please. So, one thing that they did in this initial testing was it was a level wings pull. It was not a rolling pull. That's something that we're working on now. But at this time, and all the information you read here, it was based upon, next slide please, a straight line phase pull. Next slide please. They broke it down into 4 phases to understand the report, but you'll see primarily 4 phases of recognition and recovery. Next slide please. For the purists, and I'm not a pure mathematics guy, there it is, if you don't believe anybody. Next slide please. This is called, if you talk to anyone in the community, it's called the save. People will be talking and say, well, the save is what did it. I want you to read through this with me, but essentially this F-16 platform was used for earlier modifications and testing, and particularly it was used for what's called the LASTE, and it's a targeting system used to help us put bombs on target. Well, the LASTE system caused some errors in the avionics, which led to this event. So if everybody's had a chance to read step 1. Okay, next slide please. Auto GCAS initiated the recovery from that. 460 knots, 420 feet AGL. That's not a lot of room, right? 13 degrees of dive. Next slide, please. Bottomed out at 290 feet. Next slide, please. However, the pilot, not recognizing, when they got back to base, they thought they saved the plane. But as you go through on the after-test analysis, they found out that, yes, it would have gone through the ground. This is a save, it's a confirmed save, and obviously you could never ethically try this with a human being sitting in it. So when you hear people talk about it in the community, this is a save, the save. Next slide, please. The consensus then, the human being has become the limiting factor. Not might, not maybe, is. Next slide, please. PALS. Okay, we got PEDS down here. Anybody? Next slide, please. Just go to the front of the manuals, the FIH, and you'll see these. Next slide, please. I don't want to drag you again through the specifics of the program. However, note this is what they went into, but the bottom was the big thing. They stood on the desk and said, do not give these meat servo actuators a chance to shut it off because they will. So they did not. The perfect auto GCAS system, no shut-off button. Next slide, please. First, do no harm. We all know that as doctors. I thought that was fascinating when I read their report. Do no harm. We can't make things worse. Next slide, please. And to do that, they had to make sure that the system had even more integrity and fail-safe, that when it said something was wrong, it was wrong and it wasn't a mistake. Also, it couldn't be a nuisance, which I have a few slides to share with you on that. Next slide, please. Phase 1, 2, and 3, like any good system, right? You have a plan. Next slide. 20 years of development we talked about. Over 2,500 recoveries with this system. Obviously at higher altitudes and safer, including the save. Next slide, please. The nuisance was a big thing. They thought for sure the aircrew would not take this, so they did extensive nuisance testing, which I'll show you more about in a second. And I should have made this as part of the question. Do you think it was altitude above the ground or how much time they had was what was characterizing a nuisance to a pilot? Any guesses? Show of hands, altitude, time. Okay, more time. Next slide, please. Again, as they walk through it, the system must be nuisance-free, period, dot, or else this is not going to work. We can't sell it. Next slide. They did some testing just to see how quickly we tune things out. It's the human factor side. Next slide. So this is the nuisance trials themselves from 97 to 98 only, 21 test pilots. 1,300 recoveries on that, 145 runs, on smooth terrain, by the way, not through mountains. Next slide. They characterize that when does the pilot consider it to be a nuisance versus not. I'll give you a moment to read through that. Most importantly, Anxiety level. Characterized by what? Next slide, please. So the data started to show, yeah, when is the pilot saying it's time to pull up? When is the machine saying it's time to pull up? And what are we calling that? What is that value? 0.5 second delay, but what does that really mean? Next slide. They gave them surveys when they got back and they said, tell me how scared you were before you finally maneuvered that plane. This is the survey they filled out after each flight. Next slide. And the data showed the magic number is 1.5 seconds is when we become uncomfortable. Doesn't matter how high we are. Next slide, please. Time available. Next slide. Reliably, this program was able to perform at 500 feet, sometimes 125 feet over smooth terrain. They're trying to work on rough terrain with that now. But clearly, the resolution, we would have known without the testing that it was effective, right? Next slide. ACLS. And for our Navy brethren in the room, next slide, please. Yeah, I didn't know that one. Next slide. And next slide again, please. This is the raw data, but notice anything with negative is bad. That means we've touched the ground. And so when they went back in to figure out what was going on, next slide, you'll see the difference between the actual heads-up display of what the pilot was seeing versus what the machine thought it was seeing. And those were some data points that were inaccurate that have been worked out since. But that's the reasons for those two bad indications. Next slide, please. A lot of that came out of the embedded GPS INS system where they incorporated the old school and new stuff to make sure that the plane knew where it was. Next slide. So that was the final numbers. Next slide, please. What we'd already talked about, but what I want to focus on is improvements in DTED, this arc second concept. Next slide, please. I'll show you that's where they started. Those are pretty large representations of the smooth Earth, as you would agree. Next slide. But then as the data got better, down from 6 to 3 to next slide, 1 arc second, the fidelity got better. So the machine knew what it was dealing with. It was flying through canyons, et cetera, instead of smooth ground. Next slide. Now that makes a little bit more sense. Next slide. I won't go into too much on the fail-safe, but the fail-safe was if it doesn't have integrity and we can't trust it, then we're not going to use it. Next slide. ATC? Next slide, please. I can't believe. No oncologists in the room? What are we thinking here? Okay, next slide. So, come full circle. All this data has been done. Go back to our initial study and they say in 2006, fully fund it and do it. Next slide, please. These are statements of fact they made. Otherwise be lost. Next slide, please. Based upon historical trending data, this is the point. People say, well, maybe we won't make the same mistakes. Reliably, we will. Next slide, please. So, Secretary Rumsfeld, 2006, we're going to fund this. It's high priority. Next slide, please. Continuity, Secretary Gates, now 2007. Somebody has the reins, new guy in charge, still says this is high priority. And then we heard yesterday from General Travis, same. Next slide, please. These numbers do not include anything past 2009 due to the study, but of course in the United States we've had some additional losses where F-16, F-22, likely it'll be falling in this data soon. Next slide, please. There's Navy. And this is all since that was published, arguably preventable. Next slide. 62 to 1 return on investment, 172 lives, 209 aircraft. Is it worth 62 to 1? Even in times of tough economic issues. Next slide, please. This is where we're at with the transition. There's phases 1, 2, and 3, as we talked about before, and we're trying to get it down to 50 feet above ground level. Next slide, please. But if they can incorporate the air-to-air, the air-to-ground, and then put them into one machine, you've got 78 pilots, 136 aircraft, $6.7 billion. Next slide, please. How they came up with the assumptions, it was the life cycle, the service life of the aircraft, not based upon how much each aircraft costs. It's how long we think the aircraft is going to be in the inventory for current day value. Next slide. And then we'll run through these quickly. I'll let you scan them, but you'll see this is the estimated losses if we don't incorporate this. Next slide, per airframe. There's the F-35s. Obviously, with the large purchase around the world, it's a lot bigger numbers, 2.4 billion. Next slide. 16s, it's an older legacy system. We're talking 843 million. We're in the millions instead of the billions. Next slide. And 18s. Next slide. It's interesting. The return on investment of 6.2 to 1 was incorrect. That was something that I talked about with Colonel Derek Knight last night. That was originally based upon F-16s with older radar versus the new radar. So that's the discrepancy. Next slide. And again, the numbers. Next slide. Next slide. And again. Force enhancement, obviously, if we can get into high threat areas, evade radar, get lower, fly in even lower than my British friends. Of course, we fly, you all fly at 100 feet above the ground. Well, if we can get at 50 feet and the plane's helping you do it, you can evade some of those radar systems. It is a force enhancement option. Next slide. What's next? Yes, they're testing it. You might not realize you're not in a good seat position and you don't know you need to get out, but it knows. And if it says we can't save the plane, but we're still going to save you. Next slide. Full circle now, back to those handheld mobile devices that they're testing on UAVs. This is it. That's the plan. We're not just going to let these assets, although they're unmanned, go to waste. We're going to save them as well. They're valuable assets for the governments that purchase them. Next slide, please. The bottom line, it works. It's 98% effective. It is the future. It has to be done. The return on investment is worth it, let alone the lives it will save. Next slide, please. All right, here we go. You know, when you go through medical school, you always hear that C's the answer. Next slide. That's it. And then one more for the overall questions. Next slide, please. 1910, Scientific American. How far we've come in 100 years. Isn't that amazing? Next slide, please. I love this. It's true. Two most useless things to you. I couldn't find anything exactly the same in medicine. I'm working on it, but I have found out like if you lose the battery, you're trying to intubate, you can't get a light, that's up there. So, you know, a dead battery might be there. Next slide. So, sorry I went over a bit, but any questions? Yes, sir.
What if you want to eject into control the ejection so that what they're going to do? Because you cannot disengage if you said that.
You're saying if you want to have a controlled ejection procedure, you still can leave the aircraft. It's not pending on permission from the system.
And the aircraft, how will respond when it goes to collide?
I understand what you're saying. It'll continue to fly until it runs out of gas then, right? Because it doesn't want to hit the ground. That's valid. I've not read anything on specifics of whether they would put an override on it that says once you fire the seat, then perhaps it would make sense that it would actually dive towards the ground in the bailout area. But I've not read specifics on that. Great question. Anyone else? Okay, thank you for your time.
What the answers are. Ooh, that's a big change. Didn't expect that.